So, hello everyone. Nice to see you. If you have any questions, the URL and code are here. It's the same as for the other sessions, basically. So, if you have questions, I can answer them at the end. First, I have a question for all of you. Just shout if you have the answer. What are we seeing on this screen? DRAM units. Anything else? CPU. Something like that, yeah. I don't know exactly, but it's all chips, sensors, computing, storage, and that's what we're going to talk, or what I am going to talk about in the next 50 minutes. So I joined ASML about 2 years ago, and I learned a lot on how computer chips are created. And I also realized myself, like, hey, I've been using chips my entire life. You all do. I mean, they're in your laptop, in your phone. But I had no clue how they were actually made or what the challenges are in creating those chips and how Java software was involved. So while I learned more, I thought it would also be interesting to share some of that knowledge. So this is why I created this session. So it's not completely a Java session. Java is at the end. As an example, I will use the project I'm working on where we use Java. But a lot of the content is about how chips are created. So if you really want a Java session, you can still run away. Don't worry, I can't see you with all the lights, so that's fine. So let's get started. So nowadays, we have a lot of chips. I already mentioned your laptop and your phone, but I mean, nowadays we have these smart ovens where you can already heat your meal while you're driving home and things like that. It's getting more and more. Even a car, it has so many chips already in it, it's almost crazy. And the expectation is that it will continue to grow like crazy. Like now we have roughly 5 connected devices per person, and it will go to 41. So I hope we don't need to carry them all in our bags because that will be quite heavy. But it shows how much this industry is going bigger and bigger. Now we hear AI. To do AI, you need a lot of chips, fast chips. So it's continuously evolving. Anyone an idea what's shown in this picture? A wafer indeed. And what's on the wafer? The Duke indeed, the Java logo, Java mascot. And you see about 564 here, or exactly 564. If you don't trust me, count them. That's more or less the amount of chips you can have on such a wafer. It differs a bit. Sometimes, for example, for RAM chips or for CPU chips, the amount of chips you can do on one wafer differs. This wafer, by the way, is 30 centimeters in diameter, so it's about this. It's quite small. And on that, all those chips are created. And in reality, I nicely put them all inside the wafer. In reality, they actually go over the edges, and those, yeah, they simply don't work. But still, that's the way how they are produced by our customers. So maybe good to explain. The company I work for, we don't create chips. We only create machines. And all the big semiconductor manufacturers like TSMC, Intel, Samsung, they use our machines to create chips. And those chips, they contain a lot of transistors. And this is one that you can still see. Nowadays, they're really, really small. And a transistor has a drain, a gate, and a source. It's a bit like a water tap. Water comes in, water flows out, and you can control the amount of water that flows out. Transistors work the same, but then with electricity instead of water, else they break. Probably a lot of you have heard about Moore's law. There are a lot of different ways to explain it. Probably the easiest is that the number of transistors on a chip doubles every 2 years. And that's already happening since the 70s. And it's a bit crazy, right? What other industry do you know where things double every 2 years? I mean, cars aren't getting twice as fast every 2 years. Buildings aren't getting twice as tall every 2 years. But still, for transistors, after all these years, we managed to still achieve this enormous growth. So do you have any idea how small transistors are nowadays? So I put some example numbers here. 1 million nanometers is 1 millimeter, to put it in perspective. How big do you think transistors are nowadays? Just shout. 2, 4, 42. It's below 10 already. It depends a bit which transistors you have or which machines you use, but it's already below 10, so it's super small. And that's the level of detail what we are working with. So why do we want smaller transistors? Let's imagine you have the book, maybe you know it, it's The Lord of the Rings. Maybe you've seen the recent Amazon series. I won't discuss it here, but if you join for drinks later in the evening, we can discuss it. This Lord of the Rings book has about 1,100 pages. If you would print that with 13 nanometer precision, which is relatively big still for us, you could print it on one sheet of A4 paper, 2,625 times. That has some benefits. It's easier to transport because you don't need to transport these big books. Of course, you need something to magnify it then, but I mean, that's another challenge. And if we compare that to the chips that we have, I mean, if we have SSD disks that can contain twice as much information as before, yeah, that's better. You can easier ship it. Instead of shipping 2, you only need to ship 1. Smaller transistors also means less power consumption. But that, of course, I mean, if it's smaller, we also use more, so that power consumption then is in the end used to create even faster chips often. But still, it has many advantages to go towards these smaller chips. And it all begins with silica sand, which is there in abundance. It's not like gold or diamonds. You can find it almost everywhere. You can even find it in golf courses. They use it as well. So if you see people digging up golf courses, then maybe we get a shortage of silica sand, but for now, we're fine with that. That silica sand is heated really hot, and then they create these things called ingots. And it has this weird shape because they pull it out of that really basically fluid sand, and then it gets this shape. This ingot is then basically sliced horizontally, and then you get the wafers, like the one we saw with the GeeCON. This is a front opening universal pot, also called a FOUP, contains 25, and this is the way they're normally transported inside a factory. So it's not that people walk around with a single wafer, they're automatically transported in boxes like this. To give some more details on these wafers, one machine can produce up to 300, or work on up to 330 wafers per hour, and it will print on only a single layer, as we will see later. A chip can have up to 200 layers, depending on the chip. And yeah, in the end, you can have about 140 million transistors per square millimeter, which, yeah, it sounds insane, right? At least for me, it was really insane when I first heard how much we can print on such a small surface. And it works a bit like the 3D printer. You maybe have one at home. It prints layer on layer on layer with transistors or connections. But then it does that at a bit more accuracy than your home 3D printer because you can compare it to driving on a line like this. If you drive on it for 300 kilometers, turn around, drive back for 300 kilometers, you can only deviate a maximum of 2 millimeters. That's the precision we are printing with in like real numbers instead of nanometers or even smaller. And then when we have that wafer gets coating, chemicals are put on top of it. We call that resist or photoresist. You see this automatically happening. This is also where the interesting part starts. So this is a machine sold by another company. It's not from our company. So there are different machines involved in the process from different companies, and they all work together, basically. It's like a conveyor belt with wafers going from one machine to the other. And then it goes into this machine. So this machine is used to print these different layers. It's a huge machine, contains about 450,000 parts. If you want to transport it, it requires 20 trucks and 3 fully loaded Boeing 747s. And the newest generation will set you back about 300 million. So it's a really advanced machine. Some even say it's more advanced than space shuttles and things like that. Yeah, I can't judge that. And then that wafer goes on the wafer table, the thing you see here. Normally people aren't looking at it. It's an automated process. And that wafer table, the wafer is actually floating on it. It's a magnetically levitating wafer table. Because if they would clamp the wafer, it would already bend a little bit, which results in less functioning chips, basically. So we do everything to make sure we produce as many chips and as many functioning chips as possible. And after this, basically now you see a wafer. It had that chemical coating on top of it, which we saw in the previous movie. And now we need some light basically to shine on that chemical coating. And for that we use EUV light, and I'll show you how it's created. So what we saw here was a laser amplifier, which actually, when we saw the big machine, the laser amplifier wasn't even part of it. It's in the basement. It's also huge, contains hundreds of thousands of parts as well. And that laser amplifier amplifies the laser to 40 kilowatts. Then the laser beam travels for 30 meters through the machine. And then it hits molten droplets of tin that are traveling at 70 meters per second. And it hits each droplet of tin twice. First, softly, so that it gets the shape of a pancake, and then it hits it hard, and then that droplet of tin will result in plasma, which emits ultraviolet light, extreme ultraviolet light. So it's crazy to imagine, right? At 50,000 times per second, droplets of tin are hit twice, without tin splattering around in the machine and things like that. This is how it looks like in the video. It's not a UFO, it's a droplet of tin that's being hit twice. So it's quite weird process. And it's actually that plasma that's being emitted, it gets extremely hot, comparable to the surface of the sun. So then hydrogen gas is used to remove the temperature, or to reduce the temperature in the machine, and also to remove some tin particles that might be left behind. And then that extreme ultraviolet light needs to go through the machine. And to steer it in the right direction, we use mirrors. But this is not like the mirror you have at home. These are specially created mirrors of more than 100 layers of special chemicals to make them as smooth as possible. If you would create these mirrors the size of Germany, the biggest bump would be 1 millimeter. That's how smooth they are. And then it travels around. So here basically, let's see. Here the EUV light comes out. So in the bottom here, what you cannot see, there is the laser machine. EUV light goes up and down via the mirrors. And in the end, it comes here via a reticle. And on the reticle, it contains the pattern. And from that, light goes further in the end to the wafer. So what's that reticle? A reticle is a bit like a stencil or a template. Maybe you've used one of these when you were younger. You could draw in the open surfaces, and where it's closed, you cannot draw. With a reticle, it's the same. The reticle has the pattern, how we want to have the chip, and then the EUV light at some points can shine through that stencil, and at some points it cannot shine through the stencil. So it works the same, but a reticle is a bit more expensive. They can cost up to $250,000 each. And then what actually happens is that continuously the position of the wafer is being adjusted. It needs to be at the exact right position. So that happens 20,000 times a second, the checking and correcting. And then at the same time, the reticle and stage and the wafer stage, so the reticle stage contains that reticle with that pattern in it, and the wafer stage contains our wafer. They move in opposite direction from each other with really fast speeds, as you can see here. And what's also interesting is that actually the pattern on the reticle is 4 times as big as the pattern which you will get on the wafer. The reason is that then you don't need to have these really detailed reticles. That would make them even more expensive. So the pattern's actually shrunk 4 times. And then it looks like this with the reticle, the different beams coming out. And this is how it works. So on the left, you actually see that it's being measured. So before we actually start printing those lines, a wafer is first measured and positioned correctly. At the same time, the other wafer that was already positioned correctly, there the pattern is already being printed on. And as soon as the one on the right is done, the one on the left will move through. This basically is done to improve the throughput. Otherwise, we first needed to basically put the wafer in the right position before we could start printing. And as you saw, even during printing, that's still being adjusted, the position of the wafer. But yeah, this is the fastest way that we could do this. And then it looks like this. So at the top, you see basically reticles being replaced by new reticles. And at the bottom, you see wafers being replaced and wafers being printed. So this creates one new layer on one of those wafers. So this is we call it lithography machine, the printing device basically that creates the chips on a wafer. And more schematically, it looks like this. So first step, we only have a wafer. Second step is we apply that photoresist. Third step is that we have that EUV light coming through the reticle, and at some points it shines through, and on other parts it doesn't shine through. And in the last part, we can decide what to do. either we keep the parts on the wafer where the light has shone on, or we remove those parts where the light has shone on. So we can choose either option, depending on what layer we make or what we want to achieve. And so everything we saw now, it's basically it's one step, one layer, and for each layer, basically this circle needs to be executed. So we have the exposure, where basically we print one layer, the photoresist, we also saw that, but after that there are more steps. We have the baking, we have removing of photoresist, etc. So it actually takes several months before a processor is done, because all those layers need to be done one by one. It's not something you can easily do in a day or something, it takes time. And here we also already see some other devices, like the YieldStar and E-beam for metrology and inspection. So we also want to see what's going on and how we can improve those parts. Maybe if you dive a bit into this, if you're interested, you can find more information on the internet. And then you will see that there are nowadays two types of machines. One is DUV and one is EUV. The stuff that I've shown you, it's based on EUV. It's a little bit different. It uses mirrors instead of lenses. With EUV, you cannot use a lens because EUV light, it quickly disappears. So if you use a lens, the light is gone. So one of the benefits of EUV is that we can print smaller features, smaller transistors basically. But the other advantage is that for DUV, for some things, we need like 3 layers to achieve some functionality. With EUV, we can print that same functionality in 1 layer. So that's of course way faster, and you can achieve more complex structures that way. And one thing I found quite interesting, so when I first heard about how EUV light was created with shooting droplets of tin, I was quite surprised that they managed to make it work once, but it runs 24/7. Continuously these machines run. And actually from all the machines we sold in the last 30 years, 95% is still being used by our customers. And the reason is that in a lot of cases you don't need those really advanced machines. If you simply have a temperature sensor or something like that, you don't need a really advanced machine to create it. You can do it on an old machine. And the benefit of the old machine is that it's maybe even cheaper. You don't need to buy an expensive machine, but they're also often faster. Because new machines, they become faster gradually. It takes some time to go to the 330 wafers an hour, while the old machines can already manage those speeds. And it's even more complex. So if you have an advanced chip, let's say the latest you have in your laptop, some of the layers, they are critical. There you want to have really small functionality, small transistors. But for the connecting layers, you don't need that amount of detail. So you could actually, for one chip, for one layer, use a really advanced machine, an EUV machine, and for the connecting layer, just use an old DUV machine. So you can mix and match those approaches. And then you get chips like this. So this is like real-looking chips, various shapes and forms. And then if we look ahead, so now we saw what we are currently doing. And now we have a small look ahead, and this is actually already in process. So we are working on high NA now. You might have heard that Intel recently already received the first machine of this. So they're currently testing it, but it takes some years before you see that you will actually get these chips in your machines. 2025, 2026 is now the expectation that these will come out. So what's that NA? If we look at some of our older machines, then we started with the picture on the left. Then you can see that the light is being scattered around a bit, and we actually want to focus the light, because then we can create smaller detail again. So in the past, some of my colleagues found out that if you put water in between, the light would be focused better. So better focused light means that you have a higher NA. So this is that water is already also in our older machines, but this is to show what that numerical aperture means. And in our new machines, we're going to do it as I'll show you in the coming slides. So we'll use new mirrors. If we look at the current generation, so the normal EUV machines, one mirror weighs 123 kilos. The new ones with high NA weigh more than 1,000 kilos. So while we print smaller and smaller details, our machines actually become way bigger with each generation. And as you can rate, they're even smoother than in the previous generation. They're also way faster. So in the new generation, the reticle will move with 32 Gs. And you can see here what it means. The one on the right is the faster, newer one. It prints way faster. And this is how the reticle looks for the old one and the new one. At first I thought it was one of these funny YouTube videos where at the end it would smash out of the machine, but apparently they made it work that it stays in the machine with 32 Gs, being able to print all the details on a wafer. And next to these technical improvements, we also get more and more measurements. We think that measuring and software becomes more and more critical the smaller we go, because on hardware we tend to reach limits. At least that's what some people think, but still we're progressing. But we get more and more measurements to correct for things. And we need those because our customers want our machines to produce as many wafers per day and as many functioning wafers a day. So that's what we try to achieve. One of the ways we do that is we use really clean rooms. So you see NASA here and the number of particles. Yeah, those people in the US are quite dirty, right? But they probably, for them, it doesn't matter. For us, we really need that cleanliness. If in our clean rooms a person enters the room, the person is actually the biggest contaminator. People working in our clean rooms and in our customers' clean room, they cannot wear perfume. The perfume particles already interfere in this process. They can already contaminate our wafers, our machines, etc. So it's really these small particles, you cannot even see them, that influence. So they have special airflows in it, make sure that everything is as clean as possible to make sure we don't have issues with our chips. But still, things can go wrong, as you can expect at these really small levels of details. So let's imagine we print one layer of these chips, and then we print another layer. You probably notice it's slightly off. It's not really what we want, but still, blocks are on top of each other. But we would like to know this, because then we could maybe correct it and make sure that the next layer is maybe a little bit to the left again. Or if the next wafer is being processed, that this line is already nicely on top of the previous line. Because if we don't do that, you can have things like this. This is called fallover. So if you go sideways too long, the lines will fall over. And you have chips that don't work, and that's not what we want. Or you could have layers that don't connect with each other anymore, or short circuit two layers with each other. So there are many different defects, basically, that you can have. And you can have defects in various places in the process. So let's imagine you have a dust particle on a wafer. Then maybe one chip isn't working, or maybe two or three if it's a big dust particle. But let's imagine you have that same dust particle on a reticle. Then every chip that's being created on that wafer basically will have the same issue. And if you process multiple wafers after each other without detecting that issue, all those wafers basically are useless. However, for some of those issues, our customers have some solutions. Let's say you create a memory chip of 16 gigabytes and one part isn't functioning. Then if they designed the chip in a certain way, they could still disable half of the memory and sell it as an 8 gigabyte chip. Then they make less money with the chip, but at least they can make some money with it. So that's what you also saw in the past. You had these Celeron processors from Intel. That was basically a normal processor with some cores disabled because not everything went completely okay. That way they can still make money, customers can still use them. But in reality, we try to have as least of these defects as possible. And for that, we measure two things. One is things on the same layer on the right top. We will call that critical dimension. And the second one is overlay. And that's basically what I already shown with these lines. We measure how far these lines are basically separated from each other, how much they deviate. And we have different machines for that. One is based on optics and one based on electrons, because you can imagine if things are only 2 or 3 millimeters, it's hard to see with your eye or even a microscope. You need really specialized devices. So let's see how one of these devices works. So you see these FOUPs here with 25 wafers in it, and then it goes inside the machine. So this is a machine for measuring how well the layers are printed on top of each other. And what you'll see here is that different colors of light are being used. And based on the reflection of the light and how much it deviates, we can measure if the layers are nicely aligned on top of each other or not. So we use quite advanced algorithms to figure this out. And then what we see is that these measurements, it becomes more and more. So we get about 31 terabytes of data per machine, and customers can have dozens of these machines. We measure almost everything in a machine, and in each machine we can correct about 100,000 parameters. So if we find an issue, we can change one of these parameters or several parameters to make sure that that issue is being removed. And one of the examples is here. This, yeah, they call it a mirror. I found it a bit weird because it's actually more than 4,000 mirrors, which are all controlled individually. So if something is wrong, we can control one or several of these mirrors to make their angle a little bit different, and in that way basically create better layers on top of that chip. So this is just one of the examples of things that we can influence in the machines. All of this data, so at the top you see various machines that are being used, both machines from our company but also from other companies, and they can transfer all that data, basically the measurements, to our platform, and then we can use that data to do something with it. And that's actually where yeah, my project is about. We try to do something useful with this data. And we do that actually on premise. It's not running on the machine but on servers located at our customers, because it's quite critical. Customers don't want to share their data, and we don't want to share our algorithms. So it's quite highly secure. We do some stuff in the cloud, but that's only for testing and not for customer data. All the customer stuff runs on premise, and this is actually, it's quite heavy machines. These machines, they have hundreds of CPUs and hundreds of gigabytes of memory to analyze all the data that we need for our platform. Yeah, our platform is called IACT, and what we basically do is we analyze the data that comes from the machine, and we try to visualize it and find the root causes so that we can yeah, improve the calibration of our machine. And we created that platform because before, all of our departments, they created different tools which look different. You needed to import data differently and separately for all of them, and they were relatively slow. And those tools were used by customer support, our colleagues at customers, and they didn't really like that. So now we created a new platform. It's started about 4 years ago, where we have like one platform which contains all the functionality. So we need to process high data volumes, but we also need to make sure that some things are generic. Like, for example, each wafer has an ID, each machine has an ID, so that's generic for all the measurements. But what is actually measured can be completely different. It can be plain text data, numbers, it can be pictures, can be AI stuff. So we need basically to support any case our colleagues throw at us. So it's like a train platform. You have one platform that can service both fast trains, long trains, slow trains, whatever. We do that based on Apache Spark. Anyone here using Spark? See a few hands, yeah? So basically what Spark does is that if you have a lot of data that you need to process, or heavy algorithms that you need to run on it, you can do it on a single machine, but then it can take quite some time. You can also try to parallelize it across multiple machines. So in this case, we have worker nodes. Each worker node is basically a different physical machine, and we distribute the work across multiple machines with Apache Spark. And in the end, we collect the results back to like the original machine, the Spark driver. On top of that, we use 3 types of plugins. We use UI plugins that basically are used to visualize the data that we have. We have data plugins to import data into the platform. And we have processing plugins that are triggered from the UI. So in the UI, I can select, OK, I want to have the data from the wafers from today that are processed by this machine, and then I want to run this algorithm, and that algorithm is then executed in the processing plugin. And these plugins are then created by the different departments that previously created separate applications. So we only create the platform, we don't create all the plugins on top of it. To give it a bit bigger view of how our platform looks like, so I already explained we use Spark for the processing plugins. We're also using it for the data plugins to import all the data. So we have a data store where the raw data is being placed. We have an inventory service with metadata, so we can faster process that one. We have a backend for frontend, which is built with Spring and uses MongoDB for storing things that are, for example, session information and stuff like that. There the UI plugins are being used. And we have a React front end, and we're also looking at doing it headless with jobs. And that basically means that jobs, they run, for example, after 10 wafers. Some job is being run to see if everything is okay, and if not, recalibrate the machine. So those will also use our platform. And then, of course, it needs to respond really fast, because otherwise the next, I don't know how many wafers have already been processed and might contain the same issue. Give a bit bigger overview on the tools and libraries we're using. We're using quite a lot of different things. Maybe good to mention, I often see these cool talks from Amazon and other big companies. They show really cool technology stack that they use. Yeah, and I never advise to use the same stack. I mean, use the things that you need at this point in time. We started with simply REST-based applications. Later, when we really needed it, we moved towards Apache Kafka for data streaming and for asynchronous messaging. But we did it gradually. So GraalVM was added later. We keep on adding stuff whenever we need it, not because it's cool and hip and told at a conference, but because we need certain features. So take the same approach, I would advise. And then, so the platform is based on Java. But the interesting thing is that most of our colleagues actually don't use Java. Our colleagues are mathematicians, physicists. People are really in those detailed algorithms written in C or in Julia or in all kinds of really low-level languages. And if we would force them to use Java, they need to rewrite their algorithms. And some of those algorithms, they're actually used in our platform and on the machine. And then they would need to maintain two separate versions. So what we actually did is we made a way to support those different languages also inside our platform. So in the plugins, you can use almost any language you want to. So we have like a wrapper written in Java, or the plugin team needs to write that wrapper. And then they can access the Julia language for whatever processing they want to do. So that way they can reuse most of the logic they already have and simply integrate it into the platform. Nowadays, AI is super hip, so I need to have a slide of AI in it, of course. But I actually found this an interesting example, because you see a lot of these things, generating text and stuff like that, but sometimes it's a bit difficult to find really useful applications of AI. And this one, I actually found it interesting. So when we, with our machines, check if certain things are okay in a layer, we can do it at a normal pace, so the one at the top, and then almost 70% of the defects can be found. If we would take more time to scan that wafer, we take 8 times as much time, we can find 100% of the issues. But that would mean that we can probably scan 8 times less wafers, because the scanning, the checking part is slower than the producing of the wafers, and that will slow down the entire process. So either you scan less wafers, and you scan them better, or you scan a lot of wafers, but with a bit less time for each wafer. And actually, my colleagues found a way to use deep learning, so they could use the same speed and almost capture 93% of the defects. So this is basically combining both things, right? Both a high defect capture rate and still having a fast speed so that you can check more wafers in the same time. To enable our plugin developers to efficiently create their plugins, we created, of course, lots of documentation. But we also created Maven archetypes and other things that they can basically use to get started. We created training materials, we give them trainings, we actually have a support team that helps them as a first-line support. And to put it a bit in perspective, I always, if you hear about platforms and things being created, like is this a one-man show? In this case, at this point in time, we have about 150 FTE involved in this platform, including management and all the other functions around it. So it's not purely developers, but it gives a bit of an indication. It's quite big, and that's only for the platform side. So all the plugin teams come on top of that. So what comes out of the platform? That's basically this. So let's see. Here we can select which algorithm we want to use. In this case, we use test TDBB. In the previous step, we already selected some wafers that we wanted to analyze, and then we get these wafer plots out of it. You're probably like, what the heck am I looking at? That was at least what I had when I first saw these. So I'll try to explain it a little bit. If you look at the top right there, you see basically all the arrows have the same color and they point in the same direction. And you see CE at the top. So CE stands for correctable errors. So if all the issues are because something is too far to the left, you can basically correct it to go a little bit to the right, and then you reach the center again, right? So that's the things that we can correct. So in the one at the top, basically if we would print a little bit like this, the next layer, we basically correct it. Then you have the ones you see here, NCE, non-correctable errors. So different colors, different directions. The color means how much it's basically wrong. So these go all directions. So it's really hard from these to fix anything in the machine. But maybe if we have a more advanced algorithm, we can find more of the correctable errors inside that pile of non-correctable errors. So that way we can gradually find more ways to improve. And this is some examples, these wafer plots. You can make all kinds of plots in it. You can put in plain text data, graphs, whatever you want. It's basically up to the plugin developers to decide what information they find relevant. So to recap, I hope this explained a little bit on how the chips are made that you're currently using on your phone, or maybe tomorrow again on your laptop. And for me, it also showed that while some people say Java is old and no longer relevant, I mean, we made the decision about 4 years ago to put this very important platform on top of Java, which requires really high throughput and really fast response times. And still, they thought that Java was the best approach for this. And I think that's also partly because of the enormous community. You have a lot of developers who are really experienced, like yourself, so it's not difficult to find people. There are also a lot of tools available from the ecosystem to check for quality, or tools like Apache Spark to parallelize the workload. And if you miss certain features, you can build them on top of it. For example, we built a feature on top of Apache Spark to measure the progress, so that we can tell our customer, okay, your algorithm is now almost 80% done, things like that. We even sometimes contribute features back to certain languages or to certain frameworks and tools, so that the entire community can use them. So I think that's what the Java language keeps it strong, is the community around it. There are probably languages that do way cooler stuff, but they don't have all the things that we have in the Java community, I think. Then I have one last video, so this may be interesting. So this is the way the wafers are being transported through a factory. It's a really short video. That was it already. Yeah, the rest was really marketing related stuff, so I cut that out. And then, any questions? I see a lot of questions. So the first one, I think, the second one and the third one, I think are all related. So the big question is, are we reaching the physical limits? And I think that question was raised already years ago, but still we managed to postpone that and still go smaller and smaller. I'm certain at one point in time we will reach those limits, but for now my colleagues are still working on new generations, like the high NA one you saw here. Those machines are being developed for years before they're actually used. And we're already now working on the next generation, which can print even smaller details. So the process is still ongoing to go smaller and smaller, but it might go down in a certain period of time. So that's also a bit, yeah, like the second one is Moore's Law still alive. Yeah, to be honest, it's only my company at this point in time, I think, or my company, the company I work for, that keeps it alive, because the fast machines we sell, the EUV one, there's no one else that can create those machines, let alone sell them. So if we cannot create the next generation of machines, I think then Moore's Law will have quite a challenge. Does designing new generation of tools require more computing power, or is it mostly overcoming physical obstacles? Yeah, I think main things are physical obstacles, like we need those bigger mirrors, we need better lasers, print smaller details. But also, like I mentioned, software is becoming more and more important. So we measure more and more, so we also need more and more compute power. So I think both are going farther and farther. Which part of chip production is consuming the most energy? I'm pretty sure, but that's just a guess. I'm not completely 100% sure, and I didn't read about it. But I guess it's the laser. It's really powerful, 40 kilowatt laser. You need a lot of energy to power them. And yeah, if you look it up, our customers, they consume a lot of the energy in their countries. So these machines, indeed, they consume quite some energy. We try to reduce it, but yeah, it's difficult. How close are limits of measurement precision? What are the biggest problems in future miniaturizations? I don't know the exact details, how close we are to the limits there. We can still measure, we can still see if layers are correctly placed on each other and how far things are off. But you can imagine if we go to printing transistors of 2 millimeters, then the measurements need to be even less than, or 2 nanometers, it needs to be less than nanometers. So in our company nowadays, I hear more and more even talks about picometers, which is even one step further. So we keep on getting smaller and smaller in that regard. Yeah, the next one is actually a good one. I forgot to explain that one. How are other languages used? So we have several ways. So you can use either JNI, or you can use Docker, like a lot of people are using, where we basically communicate from the platform via Kafka messages with the Docker container. And then in the Docker container, you can run any language which you want. So basically, we have two options at this point in time. There were some experimental options as well to do it with REST-based towards Docker containers. So yeah, there are some ways to support this. The last question. Yeah, if I answer that, I'm probably fired. And I also don't know. No, so we are working on smaller and smaller things, basically. But these things, they take time. I think between EUV and High-NA, there was 7 years or something. And even before that, they already did the research. So to give it a bit of perspective, at this point in time, our company spends 4 billion a year on research alone. So there's a lot of research going on, and yeah, we're going further and further. The question is, at one point in time, it might no longer be economically viable. These machines might be too expensive. I mean, our mirrors went from 100 to 1,000 kilos. If they go to 10,000 kilos for the next generation of machines, it will be quite difficult to transport them and use them, of course. So there are a lot of challenges in this regard, but yeah, we continuously try to improve. And for example, even in current generations of machines, we try to improve those continuously. So let's say we make a new generation, it can process 100 wafers an hour. Then the next year we try to increase it to 150 wafers an hour, and then the year after to 200 wafers an hour. The same for measurements. We try to measure more, better. So it's a continuous process where we continuously keep on improving, basically. But yeah, the details are quite secret, even if I would know them. So I think we're through it. I would say thank you all, and enjoy the rest of your day.